Hey, thanks for coming back. We're talking about relative minimum and maximum values. So we know like on a parabola, there's either one minimum or one maximum. But what happens when there's a curve and there's these mountains and valleys? Those are called relative, meaning relative to the area that it's in, minimum and maximum values. And we see these little valleys here. These are relative minimums or relative minima for plural, okay? And we see these little peaks right here and right here, and those are relative maximums, okay? If we were just looking at this on a graph and cover it up with your hand for the rest of it, it would just look like part of a parabola and that'd be the maximum, right? But the rest of the graph does other little bumps and things, so we call them relative because they're localized. Here's your official definition, which basically says that as x is increasing, that the value of the first x is less than the value of the last x. So that's a relative minimum, okay? That there's this peak of, or I should say a valley of where the values are. Okay, and if it's a relative maximum, then when x is increasing, it implies that the second value is bigger than the first. Approximating a relative minimum. Okay, so we know, remember way back when we had to graph them, we would do finding this point here was also called the vertex, right? And if we could find the vertex, we could find the maximum or the minimum, where we said x equals negative b over 2a. So hopefully that jogs your memory a little bit. But what happens when it's bigger than a quadratic function, or in this case, this is a quadratic function. So you could use, this trusty old way of doing things, or you can put it in your calculator. So what you're going to do in your calculator is going to hit your y equals key. And when I put something in a box, that's because you're pressing that button. And then when you hit y equals, under y1, you're going to write this in here. You're going to go 3, and then you're going to hit this key, which gives you the value for x. And then you're going to hit this key right here, which will square it. And then you're going to go hit minus 4, and again, hit the x key, minus 2. Once you have that, you can hit your graph button right here to see what it looks like, okay? But then you can actually use your calculator to approximate the relative minimum or maximum. So here's what you're going to do. To find the minimum or maximum, you're going to click second calc or trace. So you're going to hit the trace key, which will activate the calculator for the points. So you're going to hit second, and you're going to hit trace, which activates the calc, okay? And then you're going to find there's an option on there. I think it's option number 3, if I remember correctly. But basically there's an option, and depending on what your graph looks like, if it looks like this, you're going to be looking for the minimum. If it looks like this, you're going to be looking for the maximum, okay? So you're going to select that option, which I'm going to pull up right now, and which I can't right now. Anyway, you're going to select that option, and then when you hit enter, it's going to bring you to a picture of the graph again, and you're just going to scroll over. You're going to use these keys here, the left and right keys, to move it closer to the maximum or minimum value, okay? You're going to move it close enough to the minimum. First, you're going to put the cursor on the left side of that vertex and hit enter. And then you're going to move your cursor over to the right a little bit, and you're going to go on the right side of the vertex and hit enter again. And then when it says guess, you're going to hit enter. And when you hit enter that third time, it will literally tell you what the maximum or minimum value is. It's awesome. Okay, practice it and we'll go over that in class as well. Okay, we actually just did this, so we're not going to worry about that example. Okay, so now we're talking about step functions. So step functions, hopefully you've seen these before. It literally looks like this, where we're literally making cute little stair steps. The way that we really call step functions, though, that's called the greatest integer function, and it's noted by this right here. It's denoted by this kind of double bracket x, which tells us that we're going to be rounding. Okay, we're going to be rounding as those numbers go, and then it basically, because when it rounds, we know how it rounds up, right? That's why it jumps. So it goes from -3, or -2.9, -2.8, -2.7, all the way to -2.0001, and then it jumps up to -2, and then it goes, negative 1.9, -1.1, negative, all the way, and then it jumps up. And then here we get to 0, it goes to 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 0.9999, and it rounds up to 1. So these jump, okay? Because when we are rounding the values, when you're rounding, if x is 0.5, it rounds down to 0. So that's why when x is 0.5, that value of y stays here flat. Okay, so it rounds down. So this greatest integer function, it's kind of like your rounding down function. Okay, and the range and the domain of it means we can literally put in any value of x, so from negative infinity to positive infinity. But the range is the set of integers, right? Because the range, if you look here, and I'm going to do it in purple, the range only hits -3. It only hits -2. It only hits -1. It only hits 0. It only hits 1. It only hits 2. It only hits 3. So the range is not like negative infinity to positive infinity. The range is literally the set of values that we see, okay, which is just the set of integers, because it's literally -3, -2, -1, 0, 1, and 2, and 3, and so on. Okay, so it jumps. So now we're going to sketch. Sorry, I moved this wrong way. We're going to sketch what a piecewise function is, which we've kind of talked about this before, but now we're going to sketch it by hand. Okay, so we've got two pieces here, right? We've got 2x plus 3 when x is less than 1. And we have negative x plus 4 when x is greater than 1. So basically, we're going to be graphing two different linear equations and cutting them off, okay? So I would suggest graph this top one like you normally would, but have your eraser ready, okay? So remember, we have y equals m x plus b, where m is your slope and b is your y-intercept. So for this is the slope, and this is the y-intercept. So at 3 is my y-intercept that goes here. And if the slope is 2, remember that the slope is really 2 over 1. So we rise 2 and we run 1. So we're going to go up 1, 2 over 1, up 1, 2 over 1, and so on. And we're going to continue that pattern, okay? So basically, I'm drawing this. And then I'm going to come back with my eraser. Okay, now remember, I'm looking at when x is less than or equal to 1. So I'm going to come back at my eraser, and I know that this is x is 1. So I'm going to use my eraser. I'm going to follow it up, and I'm going to erase Whoops, it doesn't let me do that. Basically, I'm erasing anything past where x equals 1. Okay? And we also look really closely at this. It's equal to, so at 1, I'm putting a solid dot there. Okay, let's look at the next one. We'll do this one in green. So again, this is negative x plus 4 when x is greater than 1. So again, I am going to graph this like I normally would without a restriction. So remember, this is our m value. This is our b. So our b is 4. So up 1, 2, 3, 4. It starts here. And then the slope is negative 1, which if I put it over 1, it's a rise of negative 1, which means we're going down, and a run of positive, so 1. So we go down 1 over 1, down 1 over 1, and we keep going, okay? So that's that line, right? But because it's a piecewise, it starts when x is greater than 1. So we're going to literally erase anything to the left of this. We're going to erase this part, but we're going to keep this, okay? Let me see if I can do it. Oh, nope, it erased it, the whole thing. So basically, we're keeping this value at 1, and we're keeping it this way. But keep in mind, look right here. It's greater than 1, so it cannot equal 1. So on that point, we're going to have an open hole, so we're not going to fill it in, okay? And that's my piecewise function. And as we're looking, just know it goes forever, it goes forever. At 1, it changes values, but there still is a value at 1 here. After 1, it jumps, and it goes this way. Okay, let's talk about even and odd functions now. So basically, even and odd functions are basically a way of describing a function. When something is symmetric to the y-axis, remember this is the y-axis, so if it's symmetrical, we could flip it back and forth on the y-axis and it becomes itself. It's an even function. If something is symmetric to the origin, which basically means that it flips over the origin this way, okay? And it kind of actually probably rotate is a better way to describe that. That it can rotate onto itself right here. You can kind of use your fingers and flip it. If it's the same, that's called an odd function. And if it's symmetric to the x-axis right here, so you can flip it over the x-axis from here to here, we actually call that not a function. So we're going to use this representation to help us think, okay, so here we see that it's symmetrical right here. So it's symmetrical on the y-axis, so we know that this is an even function. So here we see that it's symmetrical about right here. So I could kind of rotate it onto itself. So we call that's an odd function because it's symmetrical about the origin. Here, again, it's symmetrical here, but it's not symmetrical on the y-axis. So if it's not symmetrical on the y-axis or the x-axis or the origin, we call that it's neither even or odd. And then this one here, again, it is symmetrical across the y-axis, so we call that even. But here's an official test algebraically for that. Okay, so here's the test for an even function. The test is this. If I plug in negative x for the value of x and we still get the same thing at the end and it equals f of x, then it's even. Okay? The test for an odd function is when we plug in negative x and we get the whole function but times a negative. That's odd. So let's try that, okay? So we're going to give it a test where basically we evaluate f of negative x. So if we were going to evaluate this one in part A, let's evaluate g of negative x. So we're going to end up with, so remember when we plug in this stuff, you put parentheses first, and we're plugging in values of negative x instead of x. And we're going to see what comes out of it. So negative x cubed stays negative x, and negative times negative is a positive. Now let's compare this to the original function. Are these the same or are they different? They're definitely not the same, so it's not even. If it's exactly opposite of this, then it's odd, which it is because it's the opposite of positive x cubed and the opposite of negative x. So we call this an odd function. Next one, let's look at this one. Let's use our test. Instead of h of x, we're going to test h of negative x. So we're going to go parentheses squared plus 1. So we're inserting that negative x and seeing what happens. We get back positive x squared plus 1. Let's compare this. And it's exactly the same. So we know that's an even function. And lastly, let's test f of negative x. So we're going to plug in to the original function negative x. We get negative x squared, x cubed minus 1. And if we compare the two, this part's opposite, but this is not. So this is a neither. And that's it for today. We'll see you next class.